Hello everyone, and welcome back. Today we're going to be exploring a very important theorem known as Taylor's remainder theorem. And this theorem can be viewed as a variation of the Weierstrass approximation theorem. And it says the following. Suppose that you have a closed and bounded interval a from a to b, and f maps a to r, with the m+1th derivative of that function continuous on that interval, which means that the nth derivative and everything below her are differentiable functions. Let's assume that c is strictly between a and b. Then Taylor's remainder theorem says the following. There exists a number z that's strictly between c and x such that this expression is valid. So we're expressing f of x as a polynomial. Here we have a 0th degree polynomial, a 1st degree polynomial, a 2nd degree polynomial, and so on. That doesn't look like a 2 now, does it? So we have our 2nd degree polynomial all the way up to an nth degree polynomial. So this quantity here is sometimes referred to as the Taylor approximation. Taylor approximation of f centered around x equals c of order n, right? The highest exponent in this expansion. And this little character at the end, so this is where that number z comes into the picture. This is usually referred to as the remainder term. This is the remainder term. Right? Now, if you remember Weierstrass's approximation theorem, it says that if f is just a continuous function, it didn't even need to be differentiable, then there exists a polynomial approximation to that particular function, and we can increase the order of that polynomial and get any desired order of accuracy that we desire. And this, gives us a method of constructing such a polynomial approximation. But it requires that the function be differentiable, so it can be viewed as a weaker version of the Weierstrass and also Bernstein approximation theorems. So, is this really true? So, this can be viewed as almost like the error term of this polynomial degree and approximation to our function f, but is this indeed true? So let's see if we can actually provide a nice little proof using just a couple of things that we need. So what we're going to do is we're going to define the real number r by the following statement. So we're going to have f of x is equal to the sum from k is equal to 0 to n of the kth derivative of f evaluated at c all over k factorial times x minus c to the power of n. So this is just the first part of our theorem, and then we're going to have plus some number r all over m plus 1 factorial times x minus z to the power of m plus 1, where z is some real number. And our goal is to figure out what exactly does this r need to be in order for this statement to be valid. Right? So let's see what we can get here. So we're going to define a couple of functions. So we're going to firstly define capital F of z. This is going to be equal to, similar to little f, it's going to be the sum from k is equal to 0 to m of the kth derivative evaluated at z all over k factorial times x minus z to the power of n plus r all over m plus 1 factorial times x minus z to the n plus 1. So the only difference here is I'm just replacing c with z, right? But notice that here z is the variable. So z is the variable here, which replaces c, but c here was just a constant, right? So I'm switching my focus in this statement. So x is a constant in this expression, whereas x is a variable in this expression. So our point of focus is a little bit different. And a very important connection between these two things is you should be able to see that capital F of c is precisely the same thing as little f of x, right? So that's an important thing to notice. So if this is my capital F, what is the derivative of f with respect to z? So f prime of z, i.e. the derivative with respect to z, of capital F of z. So notice that if I'm differentiating with respect to z, I'm going to have this term that has z in it, and I'm going to have this term that has z in it too. So therefore, I need to use a product rule for this first term. Now, it might help you to express this as a sum of n plus 1 terms from k is equal to 0 to k is equal to n, and then differentiate term by term. But what I'm going to do is I'm going to break the first k is equal to 0 term, which is just going to be equal to the 0th derivative of f, which is just f. And we already know that the derivative of f is just going to be equal to f prime of z. And then I'm going to put the rest of the k is equal to 1 to n terms inside of a summation. So I'm going to have f prime of z, so that's the derivative of the 0th term, and then I'm going to have, again, the sum from k is equal to 0 to n of the kth plus 1th derivative of f at z, so that's the derivative of the first term times the second term, so it's going to be x minus z to the power of k, and that should be k, by the way, it shouldn't say m. And then I'm going to do the first times the derivative of the second. So it's going to be equal to minus the kth derivative at z over k factorial. And then I'm going to take the derivative of this term here. So that's going to be equal to what? So that's just going to be equal to k times x minus z to the k minus 1. And let's actually put this in a bracket so that we don't forget that that's all being summed up from k is equal to 0 to n. And we do have some simplifications that's going to go on here. Notice that we have a k here and a k factorial there, and that's going to turn that denominator into a k minus 1 factorial. And let's not forget our lonely little remainder term, which is just going to be equal to, so the derivative of something to the n plus 1, that's going to be equal to r over n factorial. And then we're going to have x minus z to the power of n, and then multiplied times minus 1. Okay, so once we clean this up a bit, what are we going to have? So we're going to have that f prime of z is just going to be equal to f prime of z plus the sum from k is equal to 0 to n of the k plus 1th derivative at z over k factorial times x minus z to the power of k minus the kth derivative of z all over k minus 1 factorial times x minus z to the power of k minus 1. Right? And also keep in mind here, technically there should have been a minus 1. That's why that leading coefficient is equal to a minus sign. Right? So once we have this, plus our little remainder term over here, let's not forget it. Right? Let's actually bring that minus sign in front. Let's write it as minus. So minus r over n factorial times x minus z to the power of n. So once we have this, notice that we have a lot of repetition inside of this term. So that's actually just going to be a telescoping series. So if you write that from k is equal to 0 to n, you're going to realize that a lot of stuff factors out. And you're actually just going to be left with this little term right here evaluated when k is equal to n, and it might be just easier to just write out all those terms just so you see that. So once you simplify everything, including that first term, because keep in mind that's going to be occurring in that last term when k is equal to 1, then you're going to have that f prime of z, after all of that algebra is going to be done, is going to be the n plus 1th derivative of z over m factorial times x minus z to the power of m, and then we're going to have our lonely little remainder term r over m factorial x minus z to the power of m. So notice that we have some repetition here, so I can actually factor that out. So I'm going to have r prime of z is going to be equal to, let's factor out 1 over m factorial, and then we're going to be left with the m plus 1th derivative of z, and then minus r, and then x minus z to the power of m, right? So a very important thing here, keep in mind f of c was equal to f of x, in particular little f of x as well. So if that is the case, that means by Rolle's theorem, there exists some number z in between c and x, either c and x or x and c, or z between x and c, such that f prime of z is equal to 0. So let's assume that this z is actually that z that makes that happen. right? And keep in mind, x minus z can't be 0 because z is strictly between x and c, right? So if this is equal to 0, well, obviously this term can't be 0 and that term can't be 0, which means that that term must be 0 there, which means that this number r is actually equal to f of m plus 1 over z. And once we plug that into the original statement for our definition of little f, then that gives us what we call our Taylor approximation for our function. So Taylor's theorem says that as long as our function is many times differentiable, we can always approximate it to some desired degree of accuracy, as long as the differentiability is preserved or goes up to a certain order of existence. So let's see if we can construct a second order approximation to the function cosine of x, and we're going to be centering around the point x is equal to 0. So this is our c in Taylor's remainder theorem. So the first thing that we need to do is find the first few derivatives of our function. So keep in mind, f of x was equal to cosine of x, and we need at least 2 derivatives of this. Actually, we need 3 derivatives, and we need the third derivative to be continuous on our interval. And then our interval, in this case, is going to be equal to the set of real numbers. So what is the first derivative of cosine? So the first derivative of cosine is going to be equal to minus sine. The second derivative of cosine is going to be equal to minus cosine. And we don't need the third derivative, but we need to make sure that this function is continuous. That's going to be equal to sine, right? So as long as this function is continuous on r, then all is well, because this term is going to give us the remainder term for our Taylor approximation. So once we have f of x, f prime of x, and f double prime of x, then we need to get what we call our Taylor coefficients. So once we have these 3, then we're going to do f of c, or f of 0, f prime of c, and f double prime of c for our second order approximation. So the cosine of 0 is going to be 1, the sine of 0 is going to be equal to 0, and the cosine of 0 is going to be equal to 1. So that gives us our Taylor coefficients. Okay, so once we have that, that means our second term is going to be equal to f of x is equal to, so that's going to be our f of c, and then 0, that's going to be f prime of c, all over 1 factorial times x minus 0 to the power of 1, and then minus 1 over 2 factorial times x minus 0 to the power of 2, and then our third order term, which is going to be our remainder term, is going to be the sine of z all over 3 factorial times x minus 0 to the power of 3 for some z in r. Okay, so once we have this, then we have our approximation. So let's just simplify and clean this up a bit. Notice that that's going to go to 0, so we don't need that. So we're going to have f of x is equal to 1 minus 1/2 x squared. And then we're going to name this function, which is obviously a function of x, because z is just a number. And that's going to be equal to r2 of x. That's going to be our remainder term for our second order approximation. So this is our approximation term. And here, let's actually specify this. R2 of x is equal to the sine of z all over 3 factorial x cubed. And some people will actually try and find out what this actually z is, but that's just a little numerical exercise, which I'll leave for you. Now, what's so special about this term? And also for this example, I invite you to verify that the third order approximation is actually the same exact function. The only difference is that your remainder term changes just a tad bit. So let's actually look at this nth degree approximation function. So that's going to be equal to the m plus 1th derivative at z all over m plus 1 factorial, and then we're going to have x minus c to the power of n plus 1. So if you look at this just a tad bit, keep in mind this right here is just a number. So although it does have n in it, as long as it's differentiable, it's not going to diverge, right? That's a very important thing, right? So if we're assuming that it's infinitely times differentiable, that's always going to be a number for all m. So if we just look at this, this is practically just some constant c times x minus c to the power of m plus 1 all over m plus 1 factorial. So what happens as n gets really, really big? Well, the limit as n goes to infinity of this remainder term, provided that that's just a constant that depends on n, but it's bounded so we don't really care about it in the limit, is just going to be equal to what? So notice that we have a polynomial term on top and a factorial term on the bottom. So we can use probably Stirling's formula on that denominator to represent it in terms of tetrations and exponentials, and use repeated L'Hopital's rule to show that this is actually just going to be equal to 0, because keep in mind, factorials grow a lot faster than polynomials, right? So this gets closer and closer to 0, and that means our function, keep in mind, our function is going to be equal to the limit as n goes to infinity of the sum from k is equal to 0 to n of the kth derivative at our c all over k factorial times x minus c to the power of m. This, which we sometimes write as the sum from k is equal to 0 to infinity provided it converges, of the kth derivative at c all over k factorial times x minus c to the power of k. This is sometimes called the Taylor series of f centered around c, right? And there's several different Taylor series that you definitely should know, and one of them we've actually already built the first few terms for, but you can build the rest of them via mathematical induction if you prefer. But cosine x is actually going to be equal to the sum from k is equal to 0 to infinity of minus 1 to the power of k of x to the 2k all over 2k the quantity factorial. And sine has a very similar Taylor series expansion centered around 0. So it's going to be negative 1 to the power of k, x to the 2k plus 1 all over 2k plus 1 factorial. And sometimes it's useful to analyze this term by term. So for example, this is going to be equal to 1 minus x squared over 2 factorial. So that's our second order approximation that we built. The next term is going to be x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus minus and so on. And over here we're going to have x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7th over 7 factorial plus minus and so on. And there's several other Taylor series out there that you can build, but I'll leave them as exercises for you. So as already mentioned, the Taylor's remainder theorem can be viewed as a slightly weaker version of the Weierstrass and Bernstein approximation theorem that we discussed earlier in this series. The next theorem actually can be viewed as a stronger version of the bisection method for root finding algorithms, and also it can be used for finding optimal values for differentiable functions as well. And some people will also name this theorem as the Newton's iteration theorem. And it says the following. So let's assume that we have a closed and bounded interval a where f maps a to r, and let's assume that the second derivative of f is continuous on that interval. So we don't need it to be infinitely many times differentiable. We don't need f to have a Taylor series on a. We just need the second derivative to be continuous, which is a little bit more, twice more weaker of assumption than the bisection method does, right? Because bisection method just guarantee or needs our function to be continuous. Now we need our second derivative to be continuous, so we're requiring more things, so technically it's a weaker theorem. So, in order for this theorem to work, we need three things to be true. The first, f of a times f of b must be negative, so it must be opposite signs. Here, now we can invoke the existence of a c in between a and b by the immediate value theorem. Because if the second derivative is continuous, the original function is too. The next thing that we need is that this first derivative must be greater than or equal to some number m1, and that number must be strictly greater than 0. So the derivative must always be greater than or equal to 0. The reason we need this little expression here is because this number here cannot be equal to 0, else we're going to be dividing by 0 in this iteration method, and that's not good. And we also need that our second derivative is bounded above and also below, and this has to be true for all x in our domain. So we define this new number k to be equal to m2 divided by 2m1. So this is similar to the contraction constant that we discussed previously with contractive sequences. then there exists a subset of our domain B that contains our solution C, with f of c is equal to 0, of course, such that for any x1 in that subset, if we define that as our what we call initial guess for our iteration, like we did for the midpoint of our interval AB for our bisection method, if we define the iteration method xm plus 1 to be equal to xm minus fxn over f prime xm, then two things are going to be true. The first is that the limit of that iteration is going to be our solution, and we're always going to have a bound on that particular thing. And this little theorem here, theorem number 2, should reminisce you of our contractive theorem as well for sequence convergence. Right? So the proof of the second one practically follows the same thing as that mentioned theorem, and the limit of this actually comes directly from the Taylor's remainder theorem. So what I want to do is I want to jump into a numerical example to sort of see how this Newton's iteration process is going to work. So let's assume that our goal is to figure out what the square root of 7 is approximately equal to. So the first thing that we need to do is define a twice differentiable function that has a 0 of the square root of 7. So an obvious choice would be this x squared minus 7 function. There's definitely many others, but this is probably the more trivial one. So we need to make sure that all of our assumptions are met. So assumption number 1, f of a times f of b is going to be equal to 0. Well, what's going to be our a? So we know that the square root of 4 will be strictly less than the square root of 7 will be strictly less than the square root of 9. So we clearly see that the square root of 7 is going to be strictly between 2 and 3. So we can actually treat our 2 and 3 as our interval a and b. So let's define a to be equal to 2 and 3, and that's going to be our interval, and let's evaluate our function on those boundaries. So f of a is going to be equal to 4 minus 7, and f of b will be equal to 9 minus 7. So 4 minus 7 will be minus 3, and 9 minus 7 will be equal to positive 2. So they are opposite signs, so the first criteria is met. The second thing is that our first derivative must be bounded by a number that is strictly greater than 0. So let's test that. So if we see the absolute value of f prime of x, so that's going to be equal to the absolute value of the derivative of x squared minus 7, so that's going to be equal to the absolute value of 2x. That's going to be equal to 2 times the absolute value of x. Keep in mind, x belongs to closed interval 2, 3. So what can you say about those values? Well, that's always going to be strictly greater than or equal to 2 times 2, which is going to be equal to 4. And we see that 4 is strictly greater than 0, so that second assumption is met, right? So we can actually treat our 4 as our M1. The third thing is that we can find our next bound for our second derivative. So the absolute value of our second derivative, which is going to be equal to the absolute value of the derivative of 2x, which is going to be equal to the absolute value of 2. And we know that the absolute value of 2 is going to be equal to 2, and that's always less than or equal to 2, right? So we can treat our 2 as our M2, so our third assumption is met. So with all of these things, we just need to find a subinterval of 2, 3 such that this number x1 will converge to our solution. So what we're going to do is we're going to take b to be equal to 2, 3, which obviously is a subset of our domain A. Now, a more thorough discussion would have to be met. How do I know any number in this set is actually going to converge or give us an initial condition that's going to converge? That's a more deeper discussion for another time, but definitely we'll get there eventually. But at least for this theorem, one should be able to show that if we choose any number that's strictly bigger than 0, it's actually going to converge to the square root of 7. And if you pick any number strictly less than 0, you're going to converge to the negative square root of 7. And you can't pick x is equal to 0 because the derivative is equal to 0 at that point. So let's take x1 to be equal to the midpoint of 2 and 3. So we're going to start off at the same point that the bisection method does. So we're going to have x1 is going to be equal to 2.5. So our iteration Steps is going to be equal to xm minus fxn, so that's going to be xn squared minus 7 all over 2 times xn, so that's the derivative of our function at xm. And then we're going to iterate, iterate, and iterate until we get whatever level of accuracy that we desire. So using x1 to be 2.5, you can get x2, and you can find that that's going to be equal to 2.65. Iterate again, you're going to have this approximately 2.645754772. Notice that iteration 1 gives us 2.6, and obviously we have convergence there. And let's do a couple more to see sort of what's going on here. So x4 is going to be equal to approximately 2.645751311, and so on. So if you notice that we have up to here convergence for iteration 3, and actually 2.645751311, and so on, actually is accurate up to that particular decimal place. And that's just after just 4 iterations. So this definitely converges a lot faster than the bisection method does, right? And this comes as a result of the Taylor's remainder theorem and also the intermediate value theorem, and also derivatives, of course. Although there's several different interesting things associated to Taylor series that one should know, one of the more important and obvious ones is the following thing. So let's assume that we have f and having a Taylor series of this particular expression. And let's assume that we want to approximate f of x around some point a. So if we drop this remainder term, then what we have here is an approximation for f of x near a. So we have that f of x is approximately equal to f of a plus f prime of a times x minus a. And if you look at this, this actually should look very familiar to you from single variable calculus, because this is just the equation of the tangent line at x is equal to a. And some people will even refer to this as the linearization of f at x is equal to a. It's just the equation of the tangent line, which is actually not too obvious. But we can also solve this equation for f prime of a, and what you'll notice is that f prime of a will be approximately equal to f of x minus f of a over x minus a. And you're like, oh, well, that looks familiar also. That's just the definition of a derivative at x is equal to a, right? So definitely there are a lot of connections with Taylor series that we've actually already known, but sort of haven't seen the bigger picture of it all. Now, one interesting thing that you can do with this particular thing is to do a nice little substitution and replace x with, for example, a plus h, and redefine your variables to give you another method for solving initial value problems for differential equations. So let's take a look at that right quick. So let's assume that we have some differential equation. Let's assume we have y prime of x is equal to some functional relation of the independent variable and the unknown function itself, y. And let's assume that we have some initial condition y of x0 is equal to y0. So if we approximate the derivative of y in this expression, then we're going to have the y of x plus h, let's say, minus y of x over h will be approximately equal to f of xy. And if we solve this equation for y of x plus h, what you're going to have is that y of x plus h, so y of x plus h will be approximately equal to y of x plus h times fxy. Right? And some people call this update equation the Euler method for solving differential equations. So this will be Euler's method, right? Which is a first order approximation, because notice that we only took the first order term of our Taylor series. So, in case you aren't already familiar with the Euler's method, let's actually do just a quick example of this before I actually show you how Taylor's methods or Taylor series can actually help us improve the accuracy of Euler's method. So let's assume that we have the differential equation y prime is equal to x squared plus y squared, and let's assume that we have the initial condition y of 0 is equal to 1. So some of you might recognize this differential equation as a Riccati equation or a reduced Riccati equation. And let's assume that we want to use the step size h to be equal to 0.1. So not too small, but also not too large. So if we look at this particular differential equation, what are we going to have? So we're going to have that y of x plus h will be approximately equal to y of x plus h times fxy, which is going to be the right-hand side of that equation. So that's going to be x squared plus y squared. So once we use our first step size, because we have our initial condition, we're going to have that y of 0 plus 0.1, or h, so x plus h, will be approximately equal to y of 0 plus h times x squared plus that associated y value squared. And that's just a number. And once you plug in all of those numbers, you're going to have that's going to be equal to 1 plus 0.1 times 0 plus 1, which is equal to just 1.1. Right? And we can continue onwards because now we have y at 1.1, or an approximation of it at 0.1. Now we can approximate at 0.2. So y of 0.2 will be approximately equal to y of 0.1 plus h times f of 0.1 and f of 0.1, or y of 0.1, I guess you could say. So let's just write that as y of 0.1 to not confuse that with the f. And once you plug in those values, you're going to have that's approximately equal to 1.222. And we can continue in this fraction. For example, y of 0.3 will be approximately equal to 1.3753. Y of 0.4 approximately equal to 1.5735. And let's just do one more just for fun of y of 0.5 is approximately equal to 1.8371. Okay, so what exactly does this even mean? So if we look at the graph of this particular differential equation, or the slope for this differential equation, we know that y of 0 will be equal to 1. So that's the point 0, 1. Okay, so when we plug in, because y prime is equal to x squared plus y squared, and if we evaluate the slope at 0, which is going to be equal to 0 squared plus 1 squared, that's going to give us a slope of 1. So we know that this curve is increasing when x is equal to 0. And according to our values for y at different points, so for example at this point, this point, this point, and this point, what we sort of see here is that this curve is actually increasing at some particular rate. Now the fun part, can you give me the exact analytical representation of this function? That's usually not so easy, especially for this particular differential equation here. So obviously, is this approximation very good? Well, notice that I chose an approximation h of 0.1. So there is some error associated to this, right? Because the true solution might actually be this dotted gray curve here. So how do we make our approximation better? Well, we obviously would make h arbitrarily small and closer to 0, because that's actually where our approximations become more and more exact. So how can we make our Euler's method more exact without actually making our h closer and closer to 0? So let's actually go back to our Taylor series. So remember, y of x plus h is equal to y of x plus h times y prime of x. So right here is our Euler method approximation. So let's actually add another term to this. So this is going to be equal to h squared divided by 2 factorial times y double prime of x. So this would be what we refer to as a second order Taylor method. And we can add more terms to this if you want. For example, we'll have h cubed over 3 factorial times y triple prime of x. That would be what we refer to as a third order Taylor method. And obviously from here on, we're going to have a term that's going to be of order 4 and higher, right? So that's going to be our remainder term associated to whichever approximation we have. So let's actually do an example of how we do the second order Taylor method for the same exact differential equation as we mentioned before. Because notice that we need y double prime in order to use this. So keep in mind, our differential equation first order is going to be represented in the form f of x, y. So if we want to find y double prime of x, that's going to be equal to the derivative with respect to x of f x y, which is going to have both x in it and the unknown function y in it, right? But we don't know what y is, so we can't state explicitly what y prime even would be. So if we go back and look at our function fxy, which was equal to x squared plus y squared, if we take the derivative of this with respect to x, what are we going to have? So the derivative of x squared, that's just going to be equal to 2x, and the derivative of y squared with respect to x, that's just going to be equal to 2y times the derivative of y with respect to x. But keep in mind, dy over dx is precisely equal to x squared plus y squared, because that's what y prime x was equal to. That's our differential equation. So that means this is just going to be equal to what? So we're going to have 2x plus 2y times x squared plus y squared. So that's going to be our y double prime term in our second order Taylor series method. So therefore, if we write this out explicitly, we're going to have y of x plus h is equal to, or at least approximately equal to, y of x plus h times, let's write this a little bit more clearly, so y of x plus h times fxy, our original fxy, and then plus h squared over 2 factorial times the derivative with respect to x of fxy, which obviously depends solely on our differential equations. So different differential equations will have different d, dx, fxy terms. But for our particular example, we're going to have y of x plus h times x squared plus y squared. And then over here, we're going to have h squared over 2 factorial. And then we're going to have 2x plus 2y y prime, which is x squared plus y squared, right? And that's going to be our second order Taylor series approximations. So if we go back to our particular example, where y prime is equal to x squared plus y squared, with y of 0 is equal to 1 and h to be equal to 0.1, and use this particular equation to our advantage, you can actually get some more approximations, actually a lot better approximations, without actually changing your h. For example, if you want to try this on your own before I show you the answer, I definitely recommend you doing so now. So if we do 0.1, you're going to have that's approximately 1.11, so that's different than before. And then 1.139, 139, that doesn't look like a 3 now, does it? It's 139, and then 0.3 will come out to about 1.15096, y of 0.4 will come out to about, what is this, 1.160755, and so on. And then y 0.5 is approximately equal to 1.172232. Right? So definitely Taylor series method gives us a numerically sound way of approximating solutions to first order differential equations without having to actually increase the computation time. Right? Because let's assume that you're actually trying to approximate what y 0.5 is, but instead of doing a second order Taylor's method, you just do h is equal to 0.01 instead. Yes, you will have about the same order of accuracy for your approximations, but keep in mind you're going to have to go from 0 to 0.1, that's 10 steps, 20 steps, 30 steps, 40 steps, 50 steps, just to get to the same exact place I got with just 5. Right? So definitely Taylor series methods do give you a slight advantage over it. The only downside is that you have to implicitly find what y double prime, what y triple prime, y quarter prime is, and so on for all of your higher order terms if you desire to use a higher order Taylor series method for initial value problems. Anyway, these are just a few things that you definitely should know when it comes to Taylor series. More to come in the future. Hope you enjoyed the video, and I'll see you in the next one. Take care.